Hello, hi to everyone. Next we are moving to the last part of the video from bipolar junction transistor. Okay, BJT. So in this particular video we are going to discuss about the leakage current and thermal runaway. So leakage currents in transistor we are going to discuss. So first we'll take up the common base circuits. Okay. So look at here. This is a common base. Base is a common. It is a PNP transistor. It is a PNP transistor. So in this particular case, the currents, actual majority charge carriers of current, we have a emitter current is a combination of base current plus collector current. So how many currents we have? Base current and collector current combination will get the emitter current. Now the base current, the first case, the base current value you will get in terms of IE 1 minus alpha into IA. You know that formula. So I don't want to repeat once again all these how to get 1 minus alpha into IE. In the previous lecture we gave complete details related to that formulas. Okay. Second one, the collector current is in terms of emitter current alpha into IE. Okay, so these are the two current constituted by the common base configuration. The combination of base current plus emitter current is equal to combination of base current plus collector current is equal to emitter current. Now what I am doing now to calculate the to identify the leakage current. I disconnect the switch in the input side. In the case of common base configuration, what about the input current? We are giving the emitter current IE. So now what I am doing, IE make it to 0 whenever I switch is open. What will happen? Emitter terminal should be open. Whenever emitter terminal is open, so what will happen? The input emitter current is not emitter terminal is not connected to the transistor. It is left open. What are the things we have left? Base and collector. So in the base and collector, already in the transistor to working in the active region, we are giving forward bias in the input side and reverse bias in the output side. So in this particular case, base and emitter terminal is connected. This is a PNP transistor. P terminal is connected to negative. The output, that it is a reverse bias. So output junction is a reverse bias. Whenever it is reverse bias, diode concept. In the case of diode, what will happen? In the reverse bias condition, reverse saturation current will be flow. The reverse saturation current is nothing but in this case leakage current in the transistor. It is the same as one junction, same as diode. In the reverse bias, leakage current will be generated. That means that what is mean by leakage current? Due to the minority charge carriers. What are the minority charge carriers? In this case, it is a PN junction. The minority charge carriers in the p-type material is electrons. Okay, in case of n type material is holes. Due to the constitution, due to the minority charge carriers, so some current will be circulating throughout the output side. That circulating currents we are call it as a ICBO. ICBO means collector and base current whenever emitter is open. Collector and base current when emitter is open circuit, emitter current is equal to 0, that is ICBO. So ICBO is exactly reverse saturation current, same as reverse saturation current or open circuit current, same as diode in reverse bias. Okay, next, what exactly ICB will see in these two diagrams, and then I will give some important things to you. So here IE is constituted and then I is divided into alpha into IC current as well as IB current. So this is the IB 1 minus alpha into IE, and then IC is equal to alpha into IE. Now the some circulating currents will be flowing. In case of NPN transistor, this is the direction. In case of PNP transistor, this is the direction. It is upward direction, is downward direction. Based on the PNP or NPN, the direction will be decided. Here ICO, this is a leakage current. So now here ICBO exactly, it is depending upon the ICBO exactly, extremely depending upon the extremely depends on temperature, because it is a minority charge carriers. Whenever temperature increases, so thermally generated minority charge carriers are increases. So you know that ICBO, in this case of ICBO is doubled. ICBO is doubled in two cases. For example, if it is a germanium, ICBO doubled. If it is a germanium, every 10 degrees centigrade it rises. Every 10 degrees centigrade it is raising 10 degrees centigrade, ICBO values are doubled. In case of silicon, every 6 degrees raising temperature, the leakage current is doubled. These are the two cases you need to remember. In the examination, it might be chance is there to get the one of the question from this. Okay. Now, in case this is the case, so in case of temperature, it is a leakage current depending upon the temperature. So whenever it is depending upon the temperature, so finally IC is equal to alpha into IE plus ICO. That is a leakage current. Alpha is equal to IC minus ICO divided by IE. Okay. So ICO, that is a leakage current, very small compared to collector current. So I can now alpha is equal to IC by IE in general. Okay. So after that, the second case, third case, in case of IE, emitter current is equal to collector current plus base current. Okay. Now collector current IC is equal to alpha into IC plus IB. Alpha into IC plus IB plus ICO. How we will get, IC is equal to IE plus, in this particular case, IC is equal to IE is nothing but a IC plus IB. I can replace IC plus IB. Already ICO is there na, I can write it as ICO. So I will give the last final conclusion formulas. Those formulas you remember, that is enough for the examination, because very short time is there. So finally, IC is equal to final formula alpha into IB divided by 1 plus alpha plus ICO divided by 1 minus alpha. This is the formula we have to remember. This is a collector current formula. It is included in the leakage current also. Is it okay? Next thing, one more important formula here, IB. So how I am getting this formula? See here, alpha into IC, right? Alpha into IC, I am taking it to the right hand side, left hand side. So I can take the common of IC. I will get 1 minus alpha. Now 1 minus alpha in the right hand side, it is a multiplication, it is divided. 1 minus alpha, 1 minus alpha. Already ICO is there, alpha into IB already there. Okay, clear? Next, one more thing you need to remember. IB is equal to 1 minus alpha into IE plus ICO. This is the formula we have to remember. This particular formula is coming from, you know, this particular formula coming from here. IE, you can also write it as a IC, can also write it as IE minus IB. Okay, clear? Into alpha into IE plus ICO. Okay, so from that you want IB. So IB is equal to alpha into IE plus ICO. I can take the common alpha. I take the common IE. 1 minus alpha plus ICO. I coming this particular formula coming from here. Okay, clear? This is about the common base circuit whenever the leakage current will be present. What are the important points you need to remember? The leakage current is doubled every 10 degrees temperature in case of germanium, 6 degrees temperature in case of silicon. Next we are moving to the common emitter circuit. In the case of common emitter circuit, see here, in this common emitter case, the emitter terminal is a common for both input and output. So here also the minority charge carry, for example, this is an NPN transistor. In this case we consider the minority charge carriers are holes. So in this case what we do is open circuit the input, same as I don't want to repeat once again toward all the discussion. The base case what we did, the same case here also, just I will explain. So the particular switch is open circuit. Whenever this particular switch is open circuited, the input here base current, the base current is equal to 0 whenever it is open circuited. Whenever base current is equal to 0, the current, circulating currents will be, leakage currents will be ICO. These leakage currents are due to the minority charge carriers because it is a reverse bias. Whenever it is a reverse bias, due to the minority charge carriers, it will be appear in the reverse bias condition in the output side. So these currents how to calculate? So see here. So IC is equal to, the formula beta into IB. Okay, from plus leakage current, that is the output current also included the leakage current now. So that leakage current is equal to ICO. Okay, so from that, ICO, you can also write it as a 1 plus beta into ICO. Okay, so ICO already we discussed in the previous case, right? That leakage, this particular ICO is equivalent to 1 plus beta into ICO. So finally IC is equal to beta into IB plus, okay, beta into IB plus IC, this ICO divided by 1 minus alpha. ICO divided by 1 minus alpha. So 1 plus beta is equivalent to 1 divided by 1 minus alpha. That particular formula I can replace here. So just go back to the previous video and note down that particular formulas in your running notebook, or you can take, already I shared these PDFs in the Telegram channel. You can take that PDF and then go through it once. But all these derivations are not required. So finally conclusion here, the final formula we have to remember, IC is equal to alpha into IB divided by 1 minus alpha plus ICO divided by 1 minus alpha. This is the formula finally we have to remember. Okay, from that. So how we'll get this formula? See here, beta equivalent to alpha divided by 1 minus alpha. Beta is equal to equivalent of beta of alpha divided by 1 minus alpha, already we derived in the last video. And then already 1 minus alpha is also present. So just replace that, we'll get that relation. So that is the first relation you got. Second one, in the second relation, IC can also write it as a collector current. You can also write it as alpha into IE plus ICO. Already we wrote that. So from that, IB is equal to IE minus IC. Yes or no? Yes. So this is the current of IB, this is the current of IC. So all these values are substituted, the third point you will get IB is equal to IE minus IC, right? IE minus, what is IC here, ICO, that is alpha into IE plus ICO. Okay, this is the formula we have. So finally you got all the relations related to the common emitter configuration. How will this get formula? Just simple, IB is equal to IE, I wrote it as IC is nothing but this is of IC, so I can substitute here. So after that, thermal runaway. So this is also important concept. Just listen what exactly thermal runaway. So very simple. We got one relation from the above. That relation will be IC is equal to IB plus beta into IB plus 1 plus IB into ICO. Okay. So I am using that relation. I am going to explain. IC is equal to beta into IB plus 1 plus beta into ICO. Okay. So now my question here, thermal runaway means, for example, some collector current will be present. That collector current is depending upon the two parameters, beta into IB, 1 plus beta into ICO. So now what I am doing that, whenever I increases to temperature, for example, I increases the temperature for 10 degrees for germanium. So when I am increasing the temperature, what will happen? The ICO is increases, doubled. Every 10 degrees centigrade it is doubled. Whenever it is doubled, total entire effect 1 plus beta. Beta value is in terms of 500. The beta value in terms of 300 to 500. It is a high value, right? 1 plus beta is it is also doubled. It is a small leakage current, but it is doubled with multiply with 3 to 500. That means that this is value affected to the IC increases. Again, whenever IC increases, IC is output current, it's connected to the load. So whenever IC increases, whenever it is connected to the load, power constituted by the this particular IC square into R, for example. So whenever the IC current increases, whatever the power losses, the losses is nothing but heat. The power losses are heat going to be increases. Whenever heat increases, what will happen again? The 10 degrees centigrade increases to further, for example, 20 degrees centigrade. So again it is doubled. Again IC0 is doubled, and then again this particular result is affected. Again it is increases. That means that it is a repeated process. That is a thermal runaway. Thermal runaway means that whenever increases further, the transistor going to be damaged. It is unstabilized and transistor going to be damaged. That is called as a thermal runaway. Everyone is clear about what exactly thermal runaway? This is the process of recycling. The temperature increases, IC increases, temperature increases, again ICO increases, again IC increases, again temperature increases, like that. Okay. So that's what we have a thermal runaway. After that, we'll discuss a few problems related to that, then we'll end up this particular chapter. So what are the things we have? The first problem, the reverse saturation current of NPN transistor common base circuit, that is a common base circuit, is 12 microampere. Okay, reverse saturation current they provided. So common base ICBO, it is a 12.5 microamperes. Okay. Next, emitter current IE is equal to 2 milliamperes, as well as collector current IC is equal to 1.97 amperes. Determine the current gain and base. Current gain is nothing but a alpha. So alpha you need to find out. So how to find out the alpha? IC is equal to alpha into, so find out alpha. How to find out the alpha? IC is equal to alpha into IE plus ICBO. So from that, alpha is equal to IC minus ICBO divided by IE. So substitute all the parameters. You know, IC is a 1.97, ICBO is a 12.5 into 10 power minus 6, IE is a 2 milliamperes. It is a milli 10 power minus 3, 10 power minus, micro is a 10 power minus 6. You will get 0.978, that is a current gain. After that, base current they are asking. Base current is equal to emitter current minus collector current. What is emitter current? We have 2. Collector current 1.97. You will get 0.03 milliamperes. Okay, that is about the solution. After that, we are moving to the next problem. The problem number 3. Derive the expression for the current gain and leakage of a common emitter configuration in terms of current gain and leakage of a common base configuration if alpha is equal to 0.98, ICB is equal to 5 milliamperes. Calculate you calculate beta and ICO. Okay, so from that, you know, beta is equal to relation 1 by 1 minus alpha. Already you are giving alpha value, so 0.98 divided by 1 minus 0.98, that will be equivalent to 49. What about the beta value? Got 49. After that, ICEO they are asking. ICEO is equal to 1 plus beta into in the previous explanation I gave this formula. So 1 plus beta, that is a 1 plus 49 into ICO is equal to 5 milliamperes. From that, 50 into 5, 0.25 milliamperes. 0.25 milliamperes, that is a answer. Okay, so it is a printing mistake, it is a micro. So it is a micro means a 10 power minus 6, then you will get it. Okay, fine. So that is about the problem number 3. Next we are moving to the another problem number 4. So for a transistor, IB given 100 microampere, alpha DC is equal to 0.98, ICV is equal to 5 microampere. Find the values of IC and IE. I gave one formula for IC, all these conditions. IC is equal to alpha into IB divided by 1 minus alpha, okay, plus ICO divided by 1 minus alpha. Okay, what is the alpha value? 0.98. What about the IB value? 100 micro divided by 1 minus 0.98, plus what is ICO? 10 power minus 6 microamperes divided by 1 minus 0.98. So if you do that, you will get 5.15 milliamperes, the value of IC. Next, IE is equal to IC plus IB. What about the IC value? 5.15. What about the IB value? 100 into 10 power minus 6. It is a 10 power minus 3. The value will get 5.25 milliamperes is the answer. Okay, this is a way to find out the problems. So if you want to get the confidence, this what I gave the explanation about the bipolar junction transistor, 3 videos are there. The first video and second video and this third video. Once you perfect on these 3 videos, now I am going to start the next chapter, that is a transistor equivalent circuit diagram as well as transistor characteristics. So you are comfortable with that chapter if you are perfect on these 3 chapters, 3 videos. Thank you.